All right, guys, so we're going to go over the problem set from the Unit 3 review. So the first one is given in this slide, and it says a 0.120 kilogram ball is thrown at a wall at a speed of 18 meters per second and bounces off the wall with the same speed as shown. So it's going at an angle. So you want to use some trig with this one. And the way that I did it over here, I kind of described it as sort of an initial velocity. So this is like the I part, so going towards the wall, and then the final coming off the wall. So so you need to calculate kind of the momentum in each direction. So in the X direction and the Y direction for the beginning or initial value and the final. And if you notice, like the velocities are the same and it's the same angle. So the only thing that changes is the direction of the X component. So it simplifies it a little bit down for you guys. So mass is 0.12. The initial velocity is 18 at 35, and it's going up and to the right. And the next one is when it rebounds off the wall, it's 18 at 35 going up and to the left. So I just did 18 cosine of 35 and 18 sine of 35 to get the X and Y components. And then maybe I should make this a little more clear. I used the change in momentum. So delta P is equal to the final minus the initial. So the final momentum minus the initial. Again, for momentum, it's just mass times velocity, so that's not overly complicated. Also, because the mass is not changing, I just factored it out. So I basically used P equals mv twice in each direction to determine kind of the overall impulse. So for the X term, 0.12 is the mass, so that's what I factored out. And then this is the final velocity, which is negative 14.75. That's the X term. And it's going to the left, so that's why it's negative. And then in the initial one, it's going to the right, so it's positive. So it's final minus initial. And when you put that all in your calculator, you get negative 3.54 kilograms meters per second. And that's what ends up being the total momentum or total change in momentum or impulse, because in the X component doesn't change. So it's moving up at a velocity of 10.32 with a mass of 0.12, and it continues to move up afterwards the exact same way. So because the upward direction doesn't cancel, the change in velocity is 0, and 0 times 0.12 is 0. So same kind of general equation, just working through it. So that's what A turns out to be, and then they tell you the contact amount for the amount of contact it has with the ball. So you can solve for the force. So the force is just the change in momentum divided by the change in time. So negative 3.52 divided by 0.034 gives you a force value of 104.1 newtons in the negative direction or to the left. So that's the first one. The second one involved a little bit more calc, but it's similar in its ideas. So it's just using the calculus version of this. So it's got a mass of 0.42, and it's moving to the right. So it's moving to the right with a velocity that's given. So I wrote it over here, it's 125. And then a force is acting on this mass and making it, it's a time-dependent force, so F of t. And it says that this acts in the positive Y direction. So it's pushing kind of up and upward. So if you want to write this as like a J vector, you could have. I kind of avoid that notation and just think about the ideas. So so they give you this force, and it says after 10 seconds, what's the final, or what's the velocity in the Y direction? So so first off, this force is not going to make it speed up or slow down in the X direction. It's just pushing it in the Y, so it's going to turn. So the initial velocity in the Y was nothing. And all I used was the impulse equation. So the impulse acting on a particle would be the force, the integral of the force divided, or force times the small time increment that you were measuring over. We're doing it over 10 seconds, so we evaluate that integral from 0 to 10. And then you just take the integral of this term. So if you integrate that, you get 0.06 t to the q, or t to the third power divided by 3. That's the first term. And the second term becomes negative 0.1 t. And then you plug in 10 for both. If you plug in 0, it becomes 0. So I plugged in 10 for each over here, and I got the change in momentum to be 19. This change in momentum is only in the y direction, and the initial y component for the momentum is 0 because it's not moving in the y direction. So you just basically set 19 equal to m vfy, and then divide by the mass, and you'll get this positive 45.24 meters per second as the velocity in the y direction. So that's this upward velocity. In part B, it wants to know the overall velocity of the particle, magnitude, and direction. So you need to do a little bit of trig. So we said that the y component's not changing. It's going that way. And the x component is pointing up. So we're looking for this hypotenuse vector here that I drew in VF, that arrow. So you just use the Pythagorean theorem and you do the inverse tan. I think I might have forgot to do the inverse tan part, so I'll give that to you now. So for when I did the Pythagorean theorem for 125 squared plus 45.24 squared square rooted, I got 132.9. And then just working through this, solving for theta, and that's supposed to be a theta there. That's a really big font. So let me change the thing. So theta should equal the inverse tan of, again, the y over the x, just like we've done since the beginning of class with the trigonometry, finding an angle. So it's the 45 value, 45.24. And we're going to divide that by, it's supposed to be a 4, sorry. Writing with the pad is not so easy, and then 125. So the mouse pad instead of an actual stylus. So when you do that, I got, just checking my calculator to make sure I'm in the right mode, I got around 19.9 degrees. So 19.9 is the direction apart, which I forgot on the answer key. So if you missed that, that's where it is. So that's the right angle. So it's going up and to the right at 19.9 at a value of 10 seconds. As that force is continuously changing, it's going to change direction continuously and make the, basically it's making the particle turn because of that force. All right. The next one, number 3, talks about a stationary clay block, which I labeled as C. It has a mass of 3 kilograms. And it's at rest. The BB, which is 0.003 kilograms, is shot at the block, so it becomes embedded in the block, and the velocity of the block with the BB in it afterwards are the velocity of those two things together is 0.0067 meters per second. We're going to the right because that's the way I drew the BB moving. Part A asks what was the velocity of BB before it hit the block. B asks for the determine the kinetic energy of the system before and after a collision, so we're going to compare those. And then C, what type of collision is this? Really, you can jump to C because you already know it's a pi collision because the BB becomes embedded in the block of clay. So they stick together, so you know that's perfectly inelastic. You also know that if it's a perfectly inelastic collision, the kinetic energies aren't going to be the same, so you would expect KEI to be bigger than KEF. So again, just looking at the picture, we got the BB going to hit the block. Then the BB and block move together at this new speed, and I think I left out a 0, or I might have taken away a 0, sorry. Let me check on my paper here. So yeah, I might have, this might be a typo here, so I think this should be 0.067. I think if I left it as 0.0067, it wasn't moving fast enough. So anyway, to be realistic. So in the beginning, you have the BB mass times its velocity, and then the second term for the total momentum would be 0 because this block isn't moving. After they're stuck together, 3.003 is the total mass of the BB inside the block. And again, I'm sorry, I used the wrong number there, but 0.067 is what I used in my calculation. So essentially, you just solve for this and you divide by 0.003, and you'll get 67.067 for your solution there. So I'll double check that here to make sure I didn't make another mistake. So I divide that by 0.003. Yeah, 67.067 is the right number for those values. Okay, and then you're essentially going to do the kinetic energy before the collision, which is all in the BB, so 0.003, 1/2, 0.003, and then that answer from part A squared, and you get 6.75 joules of energy. And then the final would be 1/2 the total mass times the 0.067. That one that I messed up, and that you square and you get 0.00674. So those are the values for number 3. And again, like I said, the type of collision, it's perfectly inelastic or a pi type collision because of those reasons that we discussed. All right. For number 4, a piece of clay adheres to the outer edge of a wheel of radius 0.5 meters. The wheel rotates at a constant rate of 220 revs per minute. So you're trying to find what is the speed of the piece of clay. So it's just asking for overall speed. So that's like the tangential or VT, right? They give you an angular speed. So they give you omega, and it's constant, so it's not, you don't have to worry about it speeding up or slowing down. You just have to figure out what that is in a unit that is easy to convert. So revs per minute, you're going to change to rads per second. So I did that here in this first step. So 220 revs per minute. The minutes cancel and you divide by 60 to get to seconds, and then you want to multiply it by 2 pi radians to get rid of the revolutions. So if you do that, you'll get something close to 23.03 rads per second. And then it's just multiplying it by the radius to get the speed at that point that's in a linear or tangent direction. So that's 11.51 meters per second. Part B wants to know what's the acceleration of the piece of clay. So if you think about this, this is rotating at a constant angular speed. So if it's got a constant angular speed, there is no alpha. So alpha is nothing. So alpha equals 0. So if you tried to figure out the tangential acceleration AT, you would multiply r times 0, but that seems trivial because anything times 0 is just 0. So the tangential acceleration is 0. But there is a radial or centripetal acceleration. So AC, the centripetal acceleration we talked about a while ago, that's the same as AR because the radial one goes along the radius like the centripetal one does. It's the same thing, just a different name for it. So you're going to multiply, or you're going to use the equation for that. So it's v squared over r. So you're going to take your answer to A, square it, divide by 0.5, and you'll get this radial or centripetal acceleration for number 4. So again, not too bad, just kind of working through the values and dealing with linear quantities in terms of their angular ones. Okay. The next one here, number 5, is dealing with a net torque situation. So it says that there is a wheel, and I skipped to number 6 on my paper, sorry. There's a wheel that has 3 different forces being applied to it. And they're being applied at different positions. So there's a 10 Newton force, a 9 Newton force, and a 12 Newton force. And I just labeled them based on that. So they're acting at different locations away, A or B. So A is the short radius here, which is 5 centimeters or 0.05 is what we calculated down here. And then B is a longer distance. It's the whole radius of the wheel. And that's at 0.23, so, or 23 centimeters. So over here on this part, I just calculated the torque from the individual rotational kind of forces that are the forces that are creating the rotation. So before we even get into the amount of torque, I just like to figure out the directions, because again, you're gonna have to add or combine them to get the net. So this, if I pull like on this side part of the wheel is gonna rotate in the clockwise direction. So that's a negative torque. And I labeled this torque 10 because that was the amount of force that was acting on it. So this is the torque from the 10 Newton force. 9 is gonna actually make it rotate the same way. So that's also negative. So we have a negative torque from 9. And then if you pull on the string kind of here at this one, it's going to make it rotate the other way. So that 12 Newton torque is actually a positive one. So that's how I got the directions, just imagining, okay, how would this wheel spin if this was the only force, or this was the only force, or this was the only force acting. So torque 12 ended up being positive. So that's why I have a negative, and a positive here. I didn't write out the equation on my answer sheet, but it's just RF sine theta. So the radius or lever arm, the distance between the point of rotation and where the force is applied, the amount of force, and then the sine of the angle. The sine of the angle might be the part that's a little tricky for you, but the idea is that the angle is measured from the lever arm to where the force is applied. So all these forces are applied tangentially to the edge of like a part of the wheel. So there's 90 degrees here. Even though this says it's 30 from the horizontal, we don't care about the horizontal. We care about how the radius and the force line up. So all of these are 90 degrees. So that's why it's sine 90 in all of my calculations. So again, it doesn't matter. The only one that was sort of weird that you might have got tricked with was the 12 one, because they measured some angle from like horizontal. That doesn't matter. It's where the radius goes. So if you're touching at the edge of a circle and pulling in a direction that's tangent, that's your only option, is for it to be at 90 degrees everywhere where you're tangent on the circle. So sine 90s all go to 1, and then it's just multiplying the distance times the force. So negative 0.23 times 10 is a negative 2.3. Continuing on, negative 0.23 times 9 gets you negative 2.07. And then you do 0.05 times 12, which gets you positive 0.6. You add those together, and you'll get the net torque, which is negative 3.77. So that was that one. Okay. Last one says horizontal merry-go-round, which has a weight or a force of gravity. And this is a little bit different than what we've done in a little while. So you might have forgotten the force of gravity equation, but hopefully not, is a solid disk of radius 1.41 meters. So to get the force of gravity, they tell you that, and that's just mg. So you're gonna have to solve for mass, because you're gonna have to calculate the rotational inertia for this disk. So they tell you the radius, so that's r. It starts from rest, and a constant horizontal force of 49 newtons applied tangentially, so again sine of 90. At the edge of the disk, so it's at that whole radius. So the first thing I did again was calculate the mass, because you need that. And then I started looking at the other things that I was given. So I was given omega naught is 0, the force is 49, the radius is 1.41, and then if you keep reading, it says what's the angular acceleration of the disk, so we're looking for alpha. And then it asks you to calculate various ideas at a certain period of time, and that period of time for all of the answers is 2.91. So the first thing we want to do is, I also gave you the equation for the rotational inertia of just a disk, so that's 1/2 mr squared. So that's why we need the mass here to get the inertia. So if you do Fg divided by G, or 793 divided by 9.8, you'll get 80.9. And then you're going to take that idea, multiply it by 1/2, and then the radius squared, which is 1.41 squared. You'll get 79.3 kilograms meters squared for that. So for alpha, we needed to use the torque equation. So the net torque equals I alpha. So that's that. You could have done this a couple different ways, but this is probably the easiest one. I used the other torque equation, RF sine theta, because they give you how much force is being applied at a distance and an angle. So you can figure out this torque, net torque value from that. We know I, so we're going to be able to solve for alpha. That's essentially what I did here. So I'm just expanding kind of this concept. So when I did that and plugged in the values, I got 0.87 rads per second squared, because that's the acceleration. To get the change in angular momentum, you can do this a couple different ways, or what's the angular momentum at a certain point. It starts from rest, so the initial is 0. So we just need to get final. So the final is equal to the change in angular momentum, and that's just the torque times the time. So that's like the force times the time is the change in momentum. It's the same concept, it's just rotational. So we already know the torque, because that's the number we calculated up here. And we know the time, so we just multiply those together, and you get the change in angular momentum, which is the final, because there is no initial. Part C wants to know what's the linear velocity. So linear velocity is like VT, the tangential velocity, at a point on the edge of the wheel at that moment. So we know that the angular momentum is equal to the rotational inertia times this rotational speed, omega. So I use that equation here in part C. I solved for omega f, and I just took the value that I got in B divided by I, and that's going to be your angular speed. But they want the linear, so you're going to have to convert it or use the relationship that the radius times the point at which you're measuring away, which is the radius of the disk here, times the angular speed will get you the linear speed. So linear speed is something like 3.57 meters per second. And then finally, to get the tangential acceleration, it's just r times alpha. So again, relating those concepts. So we already know alpha because we calculated that in part A, and then you just multiply it by the radius. So it's 0.87 times the 1.41, and you get 1.23. So that's the entire problem review. We got through that pretty quick, so I'm happy with that. So have a good time, guys. I will see you later.